In the previous video, we learned about the fundamental theorem of calculus, which told us that if you're trying to find the area underneath a function, that if you can find an antiderivative, you would plug in the two endpoints into the antiderivative, subtract them, and that will give you the area that you're looking for. And so this right there tells us that if we want to be able to find areas, it's really important for us to be able to find antiderivatives. And this video is going to just kind of go over some of the antiderivative rules that you should know if you want to be able to do these problems well. Now, really quickly here, I want to point out some notation terminology here. So when we write this weird S symbol and we don't put any numbers on top or bottom, this is called the antiderivative. We learned about this in an earlier video. It's also called now the indefinite integral. On the other hand, when I do put numbers on top and bottom, it's then called a definite integral. So just to make sure you understand the different notation there and the terminology. With that said, you might be wondering why we're using this same kind of symbol for these two problems, and it's exactly the fundamental theorem of calculus. That's the reason why. Because when you're trying to find the area, the definite integral, the antiderivative, or the indefinite integral is going to help you do that. So regardless, this is definitely an interesting thing to see. Also, if you're wondering where that little S symbol comes from, remember when we're trying to do these problems, we do the Riemann sum, and summation, starts with the letter S. And if you write S a little bit weird, then you get your integral symbol. So that's kind of where this is coming from, in case you're curious. Anyways, now we need to learn how to find antiderivatives of whatever thing that comes along. That's what we have to be able to do for these problems. And so I gave you a big table here of antiderivative rules. And every one of them is based off a derivative rule that you've already seen and learned in the past. And now you have to learn all these. Hopefully it's not too bad, because as I said, it's just reversing all the previous rules. For example, we learned before that the derivative of sine x is cosine x. So what that means is if you reverse it, the antiderivative of cosine is going to be sine, and that is right here. So every single one of these rules comes from a derivative rule you learned before. You learned before that the derivative of arctan is 1 over 1 plus x squared. And so now we know that the antiderivative of 1 over 1 plus x squared is arctan. And that rule is right here. So again, every single one of them comes from a rule that you previously learned. And you're going to want to learn all these new rules now as well. There's one I kind of separated. It's the reverse power rule. It's exactly what it says. You're just reversing your normal power rule. So for your normal power rule, it says if you're taking the derivative of something to a power, you bring the power down and multiply, and then you subtract the power by 1. So now when we reverse this, instead of subtracting the power by 1, we're going to increase the power by 1, and instead of multiplying by the power, we're going to divide by the power. And so that's your reverse power rule here. There's only one small thing you should pay attention to, is that this will work for every value of n except -1. If you try to use this rule for x to the -1 power, and you add 1 to that, you get 0, you divide by 0, it's not allowed. However, in this special case, we know what the antiderivative of 1 over x is. That's just ln x. And that's my first rule right here. Now, one quick comment about that one is that oftentimes, if you look in different books or online, they will instead tell you that the integral of 1 over x is not ln x, but ln of absolute value of x. And the reason why we talk about that is if you are trying to find the area on the 1 over x function, and you're doing it on the right side over here, then you do the antiderivative. 1 over x is ln x, no problem. Evaluate it to your endpoints, great. But the 1 over x graph is valid for negative values. And if you want to find the antiderivative over there, let's say c and d, you're going to have a real problem if you try to plug in those numbers into ln, because ln, you can't have negative numbers inside of it. The domain is only positive numbers. And so it turns out that you can still get the right answer. You can prove that the antiderivative will still work if instead of just doing ln x, you do ln absolute value x, and then when you take the absolute value of the thing and plug it in, you won't have a problem. So I wanted to point that out in case you see it elsewhere. With that in mind, when we're doing antiderivatives, I'm not going to worry too much about the absolute value sign there.